Okay, so this lesson video is going to be an introduction to how to do proof by induction. Okay, so to understand induction and what it actually means, when we did proofs in geometry, we used deductive reasoning. And then in this type of proof that we're going to be doing in college algebra, it's inductive reasoning. So to kind of understand the difference between inductive and deductive, basically, when we did our geometry proofs, we had theories that we were using, or theorems, if you remember those. We had data that we could use. We could analyze a picture, a diagram, anything like that. We aren't accepting or rejecting anything. We're proving through the use of definitions and tangible things exactly what we were trying to prove. Inductive reasoning is a little bit different way of thinking, okay? So basically we are given a specific case of something and we have a specific observation. We look for a pattern, and then from that pattern, we try to make a general conclusion, okay? We're not using like definition of parallel lines or definitions of anything weird, and it's going to be a lot of algebra actually that we use. So that's the most basic difference I could come up with between inductive and deductive. The next slide talks about it just a little bit as well. Okay, so inductive versus deductive, you can kind of read through those examples of where you would use inductive versus deductive. Again, in this class, we will be doing inductive reasoning and we'll be doing proof by induction. So if you want to pause the video and just kind of read through the different things here, feel free. Just trying to give you examples of the difference between, so you can kind of understand when it's more, correct to use inductive reasoning versus deductive. I'm not going to give you a test over these types of examples or anything. I am telling you we're going to do inductive reasoning in this class, so that's what we're going to focus on, okay? And what we're going to do is called proof by induction, okay? And it consists of two cases. The first case is the base case, okay, where we're making an observation that says that the case is true when n equals 1 without assuming any knowledge of anything else, okay? The second case is the induction step, and it proves that if it's true for the specific case that we just looked at when n equals 1, then it must be true for everything else, okay? It must hold true for the next, if we're looking at patterns, if we see 2, 4, 6, we can use inductive reasoning to get to 8, 10, 12, kind of a thing. So simply put, okay, this is a lot of wordy way to say what we're doing today. We are going to follow a few steps. They're very stepped out steps that we're going to do. We're going to find the case when n equals 1. We are going to show it's true for a random integer that we're going to call k. And then when we prove that it's true for the k plus 1 term, that's basically saying, all right, well, if it's true for this guy, the next one it'll be true for, and the next, 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 and so on forever and ever. Okay, so here we are. This is how proof by induction actually works, okay? In this example, we're going to show that the sum of the n terms equals n squared. Okay, so what we're looking at here is I have kind of highlighted what each part of this rule is. So S meaning this is going to be this is going to be a sum. S sub n is going to be the sum of the first n integers, okay? And in yellow here, I've got the value of each term, 1, 3, 5, 7, okay? And then in pink, I have the rule that if I wanted to find any particular term, so that I could actually add them all up and things like that. Our rule, you're not going to have to find the rule, okay? I will tell you, this would be the rule where, where we had a sub 1 equals n minus 1 times d. We wrote a rule. This is the rule for this series, okay? And the sum, in green here, is going to equal n squared, okay? So basically what we're saying, this is saying that if I add up the first 10 terms of this series right here, it would equal 10 squared. Okay, that's essentially what this is saying here. So our step 1, and we are going to follow these same 3 steps every single time. Okay, so our first step is our base case. That was what we talked about with our base case. Show that the statement is true for n equals 1. What that means, okay, is that this 2n minus 1 equals n squared. We're going to show it's true when n equals 1, right? So we're going to put 2 instead of n, we're going to put 1. And 2 times 1 is 2, minus 1 is 1. 1 squared equals 1. 1 does, in fact, equal 1. And I can tell you right now, every one of them that we do, the base case will be true. I'm not going to throw a wrench at you right now. We don't have time to do one where the base case is not true. So it's always going to be the true statement. So we know that you should get that. And again, all we're doing is these two equations, or the equation that we have there at the end, putting 1 in for n and showing that they're true, that it makes a true statement, okay? Step 2 is always one that seems a little weird, but it's called the variable switch. So the case that we have up here on the top is the sum for the first n integers. And then we want to switch and say, okay, if it's true for n, it should also be true for k. It doesn't matter which variable we use. So we can also say that it's true for k. So we do in step 2, we do what's called the variable switch, where we pretty much copy and paste what we have up there above, except instead of n, we're going to put k. So copy paste, that's really what we're going to do. So we're going to have 1 plus 3 plus 5 plus 7 plus dot, 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 2k minus 1 equals k squared. Okay, seems pretty simple. And then step 3 is the harder part, where you have to do a lot of algebra. Well, not a lot, but quite a bit of algebra. Okay, and so I kind of found an easiest way to think about it is if we can show what we have down here, that the show that the k plus 1 term holds true. You replace every k with k plus 1, and this is the induction part, where you're looking for that pattern and making a statement that it says if it's true for k, it's true for the k plus 1, which is just 1 more than k, which is the next term, okay? And we're going to use the following formula to help us out, okay? So the sum, let's do a little highlighting here, the sum of k terms, okay? So if we come back up here, highlighted in green all the way at the top, this green, this is the sum of the first n terms. However many terms we have in our list, if you add them together, you would do n squared, or in this case, k squared, plus the k plus 1 term, okay? So the k plus 1 term is basically going to be this guy here, except instead of k, Stacy, let me do this. We're going to put in k plus 1, okay? And then finally, it's going to equal the sum of the k plus 1 terms. Okay, so it's going to equal the sum of the k plus 1 terms, which means, let's see here, I'm going to use, maybe I'll use blue. Okay, oops, I didn't mean to do that. I didn't mean to erase or write on there. Let's use blue. The sum of the k plus 1 terms means I am going to use my k terms, except in here I'm going to put in k plus 1. Okay, so the sum of the k terms, that was just what we had originally, was k squared. Okay, so the sum of the first k terms is k, oops, I might want to use color here so I can maybe organize by color a little bit. So we'd have k squared. And again, that is because the sum of our k terms is n squared, but once we did the variable switch, it was k squared, plus, okay, and in red, the k plus 1 term. So I am just taking this guy here, and instead of k, I'm putting in k plus 1. So I'm going to have 2 times k plus 1 minus 1. Okay, all that I did is, again, is what I have highlighted in pink. I took k out and I put k plus 1. And then the sum of the k plus 1 terms, okay, so right here, instead of k, I'm going to put k plus 1. So I'm going to have k plus, oops, I kind of wanted to do that in blue, k plus 1 squared, because we took this, and instead of k, we put in k plus 1. Okay, and all we need to do is just a little bit of following our algebra rules, and if we can get the same thing on the left and the right, that it holds true, then we can be done. okay? We're not actually like solving anything to get like x equals 5. We want to have is like 3x plus 2 equals 3x plus 2. We want to have the exact same thing on the left as we do on the right. So we're just going to do some simplifying, right? So I have k squared. I'm going to bring that down. In my red, when I distribute here, I would have 2k plus 2, and then this minus 1 equals k plus 1 squared. Little box method down here. Don't forget, it is not, k plus 1 squared is not k squared plus 1, okay? We would have k squared, 1k, 1k, and 1. So we would have k squared plus 2k plus 1. Erase that so I have a little bit extra room. And when I simplify, oops, daisies, I didn't mean to do that. When I simplify this side over here, I get, combining my like terms, I get k squared plus 2k, 2 minus 1 is 1, plus 1. On the right, I have k squared plus 2k plus 1. When we get the same thing on the left as we do on the right, we can stop, and we are done. D-U-N, done. So again, all that we did was we took an equation up here where we had the sum of a series, okay, and we proved it was true for n equals 1. We changed the variable, and then this part right here, the induction part, you just have to be very careful with your algebra because this is saying the sum of our certain number of terms, the sum of our first 10 terms. If we add the next term to it, it has to equal the sum of the set of the next term, whatever it happens to be. It's kind of confusing to think about, but we just have a little bit of algebra that we have to do along with it and keeping track of what each part of our equation with our formula actually is. So let's try one more together. It's going to be very similar to this one. Okay, it's another summation, so let's look at another one. All right, we got 2 plus 4 plus 6 plus 8 plus 2n. Okay, so again, just a reminder that we've got this summation. This is the value of the nth term, okay? Or it's the, excuse me, not the value, I'm sorry. It's the rule to find the nth term, right? So this is the rule to find the nth term. The 2n, and then over here is how we find the sum of the n terms, okay? And then these are just the values of the terms, okay? So step 1, again, base case, we're going to use, we need to show that if we put 1 in for n, that those two actually do equal each other. So step 1, again, so we're going to put 1 in for n. So we're going to have 2 times 1 equals 1 times 1 plus 1. Okay, 2 equals 2. Yes, holds true. Okay, the variable switch, again, this is saying that not only does it work for n, it also works for any value. So we're going to do s sub k equals 2 plus 4 plus 6 plus ... 2k equals k times k plus 1. Okay, so we just switch the variables. Doesn't change what they represent or anything like that. And to show it's true for k plus 1, okay, that's our next thing, right? What we're going to do is we are going to say, all right, the sum of k terms. So the sum of the k terms, that was this over here. Okay, so remember this was the sum of the k terms. So if you look up here, remember, sum of the k terms was what was on the right. So we're going to put that first. So we're going to have k times k plus 1 plus the k plus 1 term, right? So this was the k term. So k plus 1 means I need to put k plus 1 in here. So I would have 2 times k plus 1 equals the sum of the k plus 1 term, which means this is sum over here. This side is the sum. So on this one, when I'm doing k plus 1, anywhere I see a k, I need to put in k plus 1. So I'm going to have k plus 1. And then instead of this k right here, I'm going to put k plus 1. And then this plus 1 here is still there, so we can't forget about that. Okay, and then again, it's all just algebra from here, where we need to make sure we end up with the same thing on the left as we have on the right. So we're going to have k times k, so that would be, let's do blue, k squared plus k plus, and then in green, if I distribute, I get 2k plus 2. On the right, I'm going to do a little simplifying here. I have k plus 1, and then in this second set of parentheses, I have k plus 2. When I combine my like terms on the left, I have k squared plus 3k plus 2. When I multiply that out on the right, like so, my k plus 1, k plus 2, is going to be k squared, k, 2k, 2, and when you combine that all, lo and behold, you get k squared plus 3k plus 2. When we get to this point where the algebraic expression on the left actually is the same as the algebraic expression on the right, we have it is true, and we are D-U-N, done. Okay, so these are just 2 examples. We will talk about them in class. I'm not going to go specifically all the way through these. If you need to go back and listen to the lesson video or specific parts of it again, please feel free to do that. Otherwise, we will do this one in class tomorrow, which again is going to be very similar to the one that we did, these 2 that we did on the video. If we have time, we will look at this one that has a fraction in it. It is a little bit more involved with the algebra and stuff, so we'll see how much time we have, if we can get to that or not. But in the meantime, we will have some additional practice with this in class. We'll do some examples, at least one more example together, and then you'll have some homework with this as well that you'll do in class so you can ask questions if you need it. Okay, good luck.